Okay, we just worked through in our previous problem here how to create an ice table. So as I move on through these next problems, I'm going to assume that you're very proficient at creating ice tables and understand how to use them to obtain equilibrium concentrations. So the next few problems here are going to kind of work on using ice tables to either, in this case, calculate what an equilibrium constant is, which is kind of that type 1 problem, or the rest of the problems are going to be more of a type 2, which is kind of your more typical problem, where you actually are given an equilibrium constant and then have to calculate equilibrium values. All right, so let's read through this problem, and then we're going to keep the same systematic steps that we've been using so far. All right, using an evacuated vessel, a small amount of graphite is heated to 1080 K. Gaseous carbon dioxide is added to a pressure of 0.458 atmospheres, and we make carbon monoxide. At equilibrium, the total pressure is 0.757, should say atmospheres. Calculate Kp. And again, notice this tells us Kp because the quantities of material that we have are given in terms of atmospheres, partial pressures. First step is always write the balanced chemical equation. They actually gave it to us for this problem, so here it is. Write the reaction quotient Qp. Now, when we're writing reaction quotients that deal with pressures, we don't write the brackets that indicate concentrations. You use parentheses and you write partial pressure of the species that you're considering. So in this case, it's the partial pressure of carbon monoxide squared again because we have a coefficient of 2 there. Graphite is not going to appear in our equilibrium expression because it's a solid, and so it's going to be over the partial pressure of carbon dioxide gas. No coefficient there, so there's no exponent. Next thing is convert all the amounts into correct units, molar, if we're dealing with QC, or atmosphere. They actually gave us all the pieces that we need, and so we're done with step 3. So those sections are what we call kind of the preliminary setup. And if you want to look at kind of this workflow diagram that's part of your textbook, we're going to parallel these steps very closely. These first 3 steps represent kind of this green region or the preliminary setup. Write the balanced equation, write the reaction quotient, and convert all of the amounts into the correct units. The next part is going to work on creating a reaction table. And a lot of times you are going to need an ice table, a reaction table, but you won't always. And we'll work through one sample problem next where you'll see that you actually don't need one. So step 4 says when the reaction direction is not known, determine the reaction direction by comparing Q versus K. So we had a few problems where we had to do that. With only reactant, the only option is to shift right. So when we did our problem here, where we kind of dealt with how to write a reaction table, that was kind of our first example. We knew that Q was less than K because we had no product. Our reaction could only shift in one direction. So again, let's set up our reaction table like we just learned about in our previous example. Equation goes on the top, so carbon dioxide plus carbon in the graphite form is in equilibrium with carbon monoxide. I'm going to write a line through graphite because it's a pure solid and not included in our ice table or our equilibrium expression. Initially, we have 0.458 atmospheres of carbon dioxide, no carbon monoxide. So we know we're going to lose some amount of this and gain twice as much of that. So at equilibrium, we've got 0.458 minus x and 2x. So now we have to find some way of solving what this is. Remember, we ultimately want to figure out what K is. So Kp is going to be equal to the partial pressure of CO squared at equilibrium over the partial pressure of CO2 at equilibrium. We need to figure out what these values are. Right now, at equilibrium, they've got x's in, so we need to figure out what this x is. So all of these problems are just going to have some way of solving for x. So this section that we did in the middle here was working on our reaction table. This purple part here deals with, well, how do you solve for x? Well, for this problem, they give us some information that allows us to solve for x. We can solve for x by using the sum of the partial pressures. They tell us at equilibrium the total pressure is this. So the total pressure equals 0.757 atmospheres, and that's equal to the sum of these individual partial pressures. So 0.757 atmospheres is going to be equal to 0.458 minus x plus 2x. The partial pressure of CO2 was 0.458 minus x. The partial pressure of CO at equilibrium was 2x. Solving for x here, x is going to be equal to 0.299 atmosphere. So again, lots and lots and lots of algebra in the next 3 chapters. So you want to make sure that that's something you're very comfortable with. Once we know what x is here, once you've solved for what x is, we can put it back into our ICE table to actually figure out actual values for these equilibrium expressions. So the partial pressure of carbon monoxide is equal to 2x. So that's 2 times 0.299, and that's 0.598 atmospheres. The partial pressure of CO2 is equal to 0.458 minus x, and that's equal to 0.159 atmosphere. So now we know, and I should put that these are equilibrium concentrations, we know these two values. So we can go ahead and solve for Kp. So that's what this step 8 is. Use the reaction quotient to determine Kp. So Kp, again, being the equilibrium concentrations of both of these, 0.598 squared, 0.159, and it's equal to 2.25. So we're going to work through a number of sample problems now that all tend to involve ICE tables, that all tend to involve using some type of a method to solve for x to determine what your equilibrium concentrations are.